Welcome back to Bite-Sized Breakthroughs, the podcast that brings you the cutting edge of technology, simplified and explained. Today, we delve into the world of neural architecture search with a groundbreaking paper that tackles the efficiency and effectiveness challenges of this field. Joining us is Dr. Paige Turner, the lead researcher on this fascinating project, and Professor Wide Spectrum, a leading expert in the field of artificial intelligence. Paige, let's start with the basics. What exactly is neural architecture search?
Thanks for having me, Alex. Neural architecture search, or NAS, is basically the process of automating the design of neural network architectures. Traditionally, this task has been done manually by experts, which can be a time-consuming and labor-intensive process. NAS aims to replace this manual process with an automated approach, letting algorithms find the best network designs for specific tasks.
Interesting. So NS is about finding the optimal structure of a neural network, not just the weights that connect its neurons, right?
Precisely. NAS focuses on finding the best combination of layers, connections, and operations within a neural network, rather than just tuning the parameters of a fixed structure. It's like finding the best blueprint for a house, rather than just decorating it once it's built.
That makes sense. But how did this field of research evolve? What were the challenges that NAS aimed to address?
Early NAS approaches, which emerged around 2016, relied on a nested optimization strategy. They would sample and train many different architectures from scratch, which was incredibly computationally expensive. Imagine building and evaluating hundreds of houses just to find the best design. This was feasible for small datasets and search spaces, but not practical for larger, more complex problems.
So the cost of training those different architectures from scratch was a major hurdle.
Exactly. That's why researchers turned to a concept called weight sharing. This involves training a single supernet that encompasses all possible architectures within the search space. Each architecture then inherits its weights from the supernet, significantly reducing the computational burden. It's like having a single blueprint that includes all possible house designs and then simply picking the parts you want for your specific house.
I see. But wasn't there still some complexity involved in this weight-sharing strategy?
Yes, most weight-sharing approaches used a continuous relaxation of the search space, converting the discrete architecture design into a continuous problem. This allowed them to use gradient-based optimization methods, but it also introduced a new set of challenges. The optimization process could become biased towards certain areas of the search space, and the weights within the supernet could become deeply coupled, meaning they were all interconnected in a complex way. This coupling could make it difficult to determine why certain inherited weights were effective for specific architectures.
Professor Spectrum, can you shed some light on these complexities from your perspective?
Certainly, Alex. The concept of weight coupling is a real challenge. Imagine a large family where everyone has to share a single set of tools for all their projects. While this might seem efficient at first, it can create issues. The tools might be optimized for one person's specific project, but not ideal for others. It can be difficult to disentangle the contributions of different individuals to the overall project, and the overall project might not be as efficient as it could be if each person had their own dedicated tools. This is analogous to the challenges faced in NAS with weight-sharing approaches. While they can be efficient, the complex interconnections between weights can lead to suboptimal results for specific architectures.
So where did this paper come into play? How did it tackle those limitations?
This paper revisits a paradigm called one-shot NAS, which aims to address the challenges of weight coupling and bias by decoupling architecture search from supernet training. It does this by training the supernet first and then performing architecture search in a separate step using the pre-trained weights. This sequential approach makes architecture search much more efficient and flexible.
But even one-shot NAS faced some issues, right?
Yes, existing one-shot approaches still struggled with weight co-adaptation within the supernet. They used a technique called path dropout, which randomly dropped edges within the supernet during training. While this helped to decouple the weights, it was sensitive to hyperparameters and complex to train. It also didn't show consistently impressive results on large datasets like ImageNet.
Paige, you mentioned path dropout being sensitive to hyperparameters. Can you explain what hyperparameters are and why their sensitivity is problematic in this context?
Sure. Hyperparameters are settings that are not learned during the training process, but are set manually by the researcher. These include things like learning rate, the number of epochs, or in this case, the dropout rate for path dropout. When a method is sensitive to hyperparameters, it means that even small changes to these settings can significantly impact the final performance. This makes it difficult to find the optimal configuration, as you need to do a lot of experimentation and fine-tuning.
So, this paper presents a new approach that tries to overcome these limitations. What's the key idea behind their innovation?
They propose a method called Single Path One Shot, SPOS. The central idea behind SPOS is to construct a simplified supernet where all architectures are single paths, meaning each architecture is represented by a single path through the supernet. This eliminates the weight coadaptation issues found in previous one-shot methods that used more complex supernets with multiple paths. Furthermore, SPOS trains this simplified supernet using a uniform path sampling strategy. This means that during training, the model randomly selects a single path within the supernet for each training iteration. This ensures that all architectures within the search space are trained fully and equally, unlike previous methods that relied on weight inheritance, which might not be optimal for all architectures.
So, instead of relying on a complex supernet with multiple paths, they're essentially training all architectures simultaneously by randomly sampling paths.
Yes, that's right. It's a much simpler and more efficient approach. They also use an evolutionary algorithm to search for the best architecture. This is more effective than the random search methods used in previous one-shot approaches, especially for larger search spaces.
Professor Spectrum, how does this evolutionary algorithm differ from previous random search methods, and what makes it more effective in this context?
That's a great question, Alex. Imagine you're trying to find the best route to a specific destination. A random search method would be like randomly picking directions at every intersection. You might stumble upon the right route eventually, but it would be a very inefficient process, especially if you're dealing with a large and complex map. An evolutionary algorithm, on the other hand, takes a more intelligent approach. It starts with a population of candidate routes and then uses a process of selection, crossover, and mutation to iteratively improve the routes. It's like having a team of explorers, each with a different route idea, who learn from each other's successes and failures, gradually refining their routes until they find the most efficient path. This makes the process much faster and more effective in finding the optimal route, especially when dealing with complex scenarios. Similarly, in NAS, the evolutionary algorithm allows for a more efficient and targeted exploration of the vast search space, leading to better architectures.
That's a great analogy. It sounds like the evolutionary algorithm is able to learn and adapt its search strategy based on the results it sees, making it a more intelligent approach than random search.
Exactly. This is the power of evolutionary algorithms. It allows for a more targeted and efficient exploration of the search space, leading to better results.
Paige, let's get into the specifics of SPOS. You mentioned choice blocks. Can you tell us more about what those are and how they work within the SPOS framework?
Choice blocks are the building blocks of our search space. They represent different architectural choices within the supernet. For example, one choice block might include different convolution kernels, while another might include different activation functions. During training, the model randomly samples one choice from each block, determining the architecture of the path that's being trained. This allows us to explore a wide range of architectural possibilities within the supernet, effectively covering a diverse search space.
So the choice blocks are basically like different modules that can be plugged into the network in various combinations. The supernet itself doesn't have a fixed architecture, but rather it allows for a lot of flexibility in how those modules are connected and arranged.
Precisely. Choice blocks give us the flexibility to explore different architectural components and configurations during the search process, leading to more efficient and effective designs. The paper actually introduces some novel choice block designs for channel search and mixed precision quantization.
Can you expand on that? What is channel search and how does it work? How does this relate to mixed precision quantization?
Channel search involves finding the optimal number of channels for each layer in the network. The SPOS approach uses a choice block where the maximum number of channels is pre-allocated. During training, the model randomly samples the number of output channels for each batch, effectively allowing for the exploration of different channel configurations without the need to train separate networks for each configuration. This is a more efficient and flexible approach. Mixed precision quantization, on the other hand, involves using different bit widths for different parts of the network. This can lead to significant reductions in memory and computational cost while maintaining good accuracy. SPOS integrates a choice block for searching the optimal bit widths for both weights and feature maps. This allows for the exploration of different combinations of bit widths during the training process, ultimately finding the most efficient configuration. By combining these two search spaces, channel search and mixed precision quantization, SPOS allows for the discovery of efficient architectures that are both accurate and resource efficient.
Professor Spectrum, what are the broader implications of this approach to channel search and mixed precision quantization? How does it impact the field of NAS and the design of efficient neural networks?
It's a very important development, Alex. This integrated approach allows for the exploration of a much wider range of design choices, including both the architecture and the precision of the network. This has significant implications for the design of efficient neural networks. By being able to simultaneously search for the optimal channel configurations and bit widths, SPOS enables the creation of networks that are more accurate, compact, and energy efficient. This is particularly crucial for deploying neural networks on resource-constrained devices, such as mobile phones or IoT devices. It also allows for the design of specialized networks tailored to specific hardware platforms and resource limitations, further enhancing the practicality of NAS.
Let's talk about the experiments. What kind of results did they achieve with SPOS, and how did they compare to existing methods?
The experiments were conducted on the ImageNet dataset, which is a standard benchmark for evaluating image classification models. They compared SPOS with various baselines, including manually designed networks and other NAS methods. SPOS achieved state-of-the-art results on ImageNet for building block selection, channel search, and mixed precision quantization search, outperforming previous methods in terms of accuracy and complexity. For example, in the building block search experiment, they compared SPOS with randomly selecting building blocks and using random search with the single-path supernet. SPOS achieved a top 1 accuracy of 74.3%, surpassing the other methods by a significant margin.
That's impressive. And what about the channel search and mixed precision quantization experiments?
They also achieved significant improvements in those experiments. For example, in the mixed precision quantization search, they compared SPOS with baselines using uniform quantization and a previous method called DNAS. SPOS consistently achieved higher accuracy with lower bit ops, demonstrating its ability to find efficient and accurate architectures for quantized networks. These results highlight the effectiveness of SPOS in finding efficient and accurate architectures across different search spaces.
So, SPOS is not only more efficient than previous methods in terms of training time and computational cost, but it also leads to more accurate and efficient architectures.
That's right. The paper also performed a detailed analysis of search cost and the correlation between SuperNet performance and standalone model performance. SPOS demonstrated lower memory consumption and a more efficient search process than other methods. Additionally, they found a strong correlation between the SuperNet performance and the performance of individual architectures, indicating that SPOS is effectively able to predict the performance of different architectures. While not a perfect correlation, the results suggest that the SuperNet is a good indicator of the performance of the individual architectures, giving SPOS a powerful advantage in navigating the search space.
Professor Spectrum, what are your thoughts on these experimental results? Are there any potential limitations or areas for future research?
The results are very promising, Alex. However, it's important to acknowledge some potential limitations. First, the correlation between supernet performance and individual architecture performance, while strong, is not perfect. This means that SPOS may not always identify the absolute best architecture in the search space. The paper also notes that this correlation seems to be influenced by the complexity of the search space. Second, the paper primarily focuses on image classification tasks. It's important to explore whether SPOS would be equally effective for other types of tasks, such as natural language processing or reinforcement learning. Overall, this is a significant step forward in NAS research, but there's still room for further improvement and exploration. Future research could focus on techniques to improve the correlation between supernet performance and individual architecture performance, potentially by introducing methods that better represent the diversity of architectures within the search space. Additionally, extending SPOS to other tasks and domains would be a valuable avenue for future research. Finally, investigating the potential of SPOS for hardware-aware NAS would be a promising direction. This could involve incorporating hardware metrics directly into the search process, allowing for the design of architectures that are optimized for specific hardware platforms and resource constraints.
Paige, what are your thoughts on Professor Spectrum's points? What are your plans for future research in this area?
Professor Spectrum raises some very valid points. We are definitely looking into ways to improve the correlation between supernet and individual architecture performance, potentially by incorporating techniques like architectural diversity sampling. We are also exploring the application of SPOS to other tasks and domains, including natural language processing and reinforcement learning. And as Professor Spectrum mentioned, hardware-aware NAS is a very exciting area. And we're looking into how to integrate hardware metrics into the search process to design architectures optimized for specific hardware platforms and resource constraints. We believe that SPOS has the potential to significantly impact the field of NAS and drive the development of more efficient and specialized neural networks for diverse applications.
I'm excited to see where this research goes. It's clear that SPOS represents a significant step forward in NAS, offering a simple yet powerful approach to find efficient and effective architectures. This has the potential to impact the field of AI in numerous ways. Professor Spectrum, what are your thoughts on the broader impact and potential applications of this research?
I believe this research has the potential to revolutionize the development of neural networks for a wide range of applications. By making NAS more efficient and scalable, we can now design specialized networks tailored to specific tasks, hardware platforms, and resource limitations. This opens up a new era of customized and efficient AI solutions. We can imagine applications ranging from more efficient and accurate mobile phone apps to more powerful and resource-efficient AI systems for complex tasks like medical diagnosis, autonomous driving, and robotics. It's an exciting time to be working in this field.
To sum it up, SPOS is a highly promising approach for neural architecture search, addressing several limitations of existing methods. It's simpler, more efficient, and more flexible, allowing for the discovery of highly accurate and efficient architectures across various domains. It also shows a strong correlation between supernet performance and individual architecture performance, providing a valuable tool for guiding the search process. This research opens up exciting avenues for the future of NAS, potentially leading to a new generation of powerful and efficient AI solutions for a wide range of applications. Thank you both, Paige and Professor Spectrum, for joining us today. This was an insightful and detailed discussion. Listeners, if you'd like to learn more about SPOS and the broader field of NAS, check out the links in the show notes. We'll be back next time with more exciting breakthroughs in technology. Until then, keep exploring, keep learning, and keep innovating.